Last screencast of the semester, and this is some synthesis practice for the final exam. And I'm not necessarily going to describe every single step of these. These are problems, some of them are ones that I'll use typically at the end of the semester. There are two that we introduced at the very beginning of the semester as part of our Chem 21 review. There are two that I did in graduate school. So it's kind of a mixture of different things. One of them came from an extra credit question from a final about 4 years ago. So the first one I think we already did previously, a previous set of examples, but you're trying to get these two halogens on meta, whereas they're both ortho-para directors. And so one of them has to go on via a diazonium salt, via a nitro group. And you do have to nitrate first to get the halogen on meta, but then you can put either halogen on first, and then whatever halogen you didn't put on directly, you put on via the diazonium salt. So in this next one, we have to add these two alkyl groups to this carbonyl carbon, which is electrophilic. And so any nucleophilic source of carbon is not going to be compatible with a carboxylic acid. We could, you might think, turn that carboxylic acid into an ester and then use a Grignard, but that's going to add two equivalents of the same alkyl group. We need two different alkyl groups. So we have to put them on kind of one at a time. And so what I did here is I used an acid chloride, which you can make from the carboxylic acid, and a cuprate, which isn't as reactive as a Grignard, and so only one equivalent of the cuprate will react with the acid chloride, and that works because this is reactive enough to react with the acid chloride, but it's not reactive enough to react with the ketone, so the reaction stops there. And then I add the second alkyl group via a Grignard, and that gives me my tertiary alcohol. And I could do these alkyl groups in either order, so I could have used the isobutyl group as the cuprate and then use methyl lithium here. So with this one, this has the nitrogen directly attached to the ring. This has a carbon between it. And you might look at this and think, oh, it would be really easy to chlorinate, but there are some issues with this being a little overly exuberant, so we have to protect that as an amide when we chlorinate. So one way you can do this is you can get this carbon-nitrogen grouping by adding a nitriol, and that has to happen via the diazonium salt. So this is the way I happen to do it. I'm sure there are other ways. So again, first I kind of deactivated that amine group a little bit by making it into an amide. And now when I do the chlorination, I'm going to get monochlorination. I'm not going to get anything weird going on, hopefully. And then I hydrolyze off the acetyl group to go from the amide to the amine. And once I have the amine, I can make the diazonium salt, add cuprous cyanide to make the nitriol. So that gives me the nitriol. And then there are several ways to go about these next couple of steps. What I chose to do was reduce it all the way to the primary alcohol, or excuse me, to the primary amine, and then do a reductive amination to make the final product. So these next two are ones that were on the first set of synthesis problems we looked at, which were those Chem 21 review problems. And I picked them because you can either make them a different way and or a more efficient way. So with this first one, we need to put a carbon-carbon bond here. And in theory, either side can be the nucleophile and either side can be the electrophile because we don't have any functionalization here. I chose to turn the left side into the electrophile. So we added HBr and peroxides to get anti-Markovnikov addition. And then we just use the cuprate and do a coupling reaction and we're done. And then here's the synthesis for that particular cuprate. And again, the reason I picked that is to demonstrate how much more efficiently we can now make this particular compound. So with this next one, we have to put a bond here, so between this carbon and what turns into that carbonyl. And remember that if you have carbonyls, you can get them from alcohols. If you have alcohols, you can get them from carbonyls. So if we make kind of our goal this alcohol, you can see how if you made the Grignard of this compound to turn this from an electrophilic carbon to a nucleophilic carbon, and then add formaldehyde, that we'll get this secondary alcohol. So aldehyde makes a secondary alcohol. So again, just like the one previously, we add HBr and peroxides, add anti-Markovnikov, make the Grignard, add the formaldehyde, protonate it, and then just have to oxidize it. So these next two are two things that I actually did in graduate school. What I was trying to do is, mostly successfully, is study the decomposition of this particular peroxide, which interestingly you can make by taking the acid chloride and reacting it with MCPBA, for which I forgot to put the chlorine. Reacting it with MCPBA in order to make that diacyl peroxide via a nucleophilic acyl substitution. So the chlorine really was incidental. It was there because we had to use the MCPBA. And so as part of this work, I had to put a carbon label on the alpha carbon to the carbonyl, so like here, and I also had to put deuteria. And what we were trying to do is show that this compound initially formed a radical pair, and then it underwent a electron transfer to make a cation or incipient cation. And so what we saw was rearranged carbon skeleton products that had clear evidence that they'd come from a radical pathway, and we actually used NMR for that. So in this first case, again, we have to add two carbons, and one of them, the inner one, has to be the C13 labeled carbon. And my research advisor was fairly cheap, and so I had to use carbon dioxide. Actually, what I had to do was use barium carbonate and add acid to it and generate the carbon dioxide that way on a vacuum line. And then I had this carbon 13 labeled carbon dioxide, and I unclamped it off the vacuum line and carried it across the lab and did my Grignard with it. So we have the ethyl bromide. We make Grignard. We add the radio label with the carbon 13 labeled carbon dioxide. Add acid to protonate that because we're protonating in carboxylic acid. And so that gives us our radio label there. Then you can reduce that with excess lithium aluminum hydride to make the primary alcohol. React this with, I happen to use tosyl chloride in pyridine, and I made this tosylate. And then I reacted this with sodium cyanide in DMSO, as it turns out, to make the nitrile. And then over a period of days, carried out this hydrolysis. This is how I know that hydrolyzing a nitrile is not an easy thing to do. I even had to use some ion exchange beads in order to get the reaction to occur at a reasonable rate at all. But ultimately that gave us the carboxylic acid, and then I was able to turn it into an acid chloride and then react it with the MCPBA to put the label in that compound. And then I put it in an NMR tube and heated the NMR probe up and proceeded to decompose my diacyl peroxide in the NMR spectrometer. So likewise, I also got to put deuterium in the same compound. And so I did this. First, I did a deuterium exchange. So this is a little bit like the deuterium exchange those of you who took Chem 24 lab did this semester with the amide, except that what we're doing is replacing these acidic alpha hydrogens with deuterium. And we do that by using, by going via an enolate. So the base makes the enolate of this, and then when it reprotonates, it actually redeuteriates, and over time you can replace all of the alpha hydrogens with deuterium. This actually took a couple of passes. So the first time I did it, it wasn't 100% deuterated. So I had to isolate the product and then add fresh D2O and let it reach equilibrium again. And then I think I had to do that a third time. It was a long time ago. I don't remember everything. I do remember that I made the NaOD by adding sodium to deuterated water, which was kind of fun. So once I had this, I used MCPBA, which we had a lot of in the lab for an obvious reason. And since the phenyl group migrates better than a primary alkyl group, I ended up with this ester. And that's how I happen to remember the relative migratory aptitudes of primary versus phenyl, by the way. And then I did a hydrolysis using, again, I had to use this deuterated water and deuterated sodium hydroxide because otherwise I was going to risk exchanging those deuteria off. And then once the reaction was over, then it's safe to protonate it and put the hydrogen there with the acid. But again, I did that just to prevent the exchange back. And then once I made the carboxylic acid, then I made the acid chloride from it, and then ultimately made my peroxide. So this next one was an extra credit question on a Chem 22 final a couple years ago, where we have to make this azo linkage. And you can make an azo linkage by using a diazonium compound with an activated benzene ring. So we're going to make that by making this purple bond because this ring is activated with the NH2 group. So we need to make that diazonium piece and this amine piece. And the rules of the game were that you had to use benzene as your source. That's interesting. You had to use benzene as your source of the benzene ring. So you had to start with benzene. So in order to make the aniline that we need for this, we nitrate, reduce, aniline. This is a little more challenging. So there are some issues with this rearranging. Also, if we tried to nitrate first and then acylate or even alkylate, that wouldn't work because you can't alkylate or acylate in the presence of this nitro group. So this is what I did. I did my acylation, then I kept that as an acyl group and nitrated to put the nitro group meta, which it has to be. And then remember that the Clemenson will reduce both this carbonyl and that NO2, so that gives us that. And then I make the diazonium salt of that, and then finally I can do my electrophilic aromatic substitution of those two compounds. So this one I picked in part because it's a nice demonstration of using one of our new organometallic reagents. And so we have a meta director, which is lovely because this is meta, but the problem is, of course, if we acylate, we're never going to be able to alkylate, at least not with a Friedel-Crafts. But it's perfectly legitimate to use a cuprate on a compound that has a carbonyl because they're going to do this coupling reaction. The cuprate is not going to react with that ketone. So I acylated, then I brominated, so I had a leaving group, and then this is the electrophilic piece, and I reacted with that nucleophilic piece, and it's done. And finally, we have this compound, which is a 1,3-dicarbonyl compound that you can make from a Claisen, and it's going to have to be a mixed Claisen. And remember, with the mixed Claisens, you don't worry about whether or not they both have alpha hydrogens. You just do a directed Claisen, although here you would have to do that anyway because both of them do have alpha hydrogens. Again, like one of the earlier problems, this is not going to go well if you try to do a Claisen on a carboxylic acid. You have to convert it into some sort of an ester first. And I chose to match this ester with the ester in the product so that I was consistent in having ethyl esters all the way through. So I make my ester via Fischer esterification, put that in a nice labeled vial someplace, and then I'm going to take the ethyl acetate, react that with LDA to convert it completely into the enolate, add my ester that I made up here slowly, hydrolyze it, and we're done.